Okay, so like you said, my name is Jeff Ford. I am a PhD student at Auburn University. I just finished my first year. And the teaching methods in this course, it's a little bit of a different talk because neither one of us taught the course. We were the students in the course. So I was there for my first year. This was actually my first exposure to IBL. Everywhere I'd done my master's and my undergrad work, IBL wasn't taught at all. And then Frank.
And so I have a bit more experience with IBL. I am, in fact, when I was an undergrad, I was a student of Gordon Johnson at University of Houston, and I actually came to this conference about 2000, I think it was 2004, 2005 was my first experience. And it was really exciting, and I got to see, all these people that teach with this method. And at that time, I was really interested in finding a grad school. Eventually, I did find Auburn. Gordon directed me there. Now I'm in a different situation. I just finished my PhD there, so I'm looking to go somewhere else. So unfortunately, I think Ed Parker took all my audience that I could petition for a job. So anyway, at this point, so I've been at Auburn. Not too much. Most of the teaching there has been through, that I've done as a TA, has been through a typical lecture style. However, a lot of the topology courses there are taught with IBL methods or more method. My research area is topology, and so I experience that a lot. However, one of the things, so in topology, you're looking at these different properties and spaces that, the properties that distinguish types of spaces. And when teaching topology at Auburn, it's very heavily focused on what's called general topology. And then you focus on things like set theoretic topology. But general topology, point set topology, this is something that this is what Moore taught originally. And it's also very good for things that have a strong axiomatic development. So analysis, geometry, set theory, and of course we've seen a lot of different talks here about the different applications and different classes that people have used Moore method or similar techniques with. So of course, as everyone knows from all the other talks, so you work on the problems, you're usually given statements of definitions. You prove or disprove things about statements of definitions. You prove or disprove things about examples or counterexamples. And you go through it, and that's how you develop your intuition. On the other hand, when you look at something like algebraic topology, going into algebraic topology, this has a very strongly, it's almost entirely, especially at the beginning, example motivated. You have a few definitions, you have to prove some things, but you don't really have the same type of structure that you would find in like a general topology course from the outside. And in other words, and one of the other things, when you think of formalization, I mean, you think about balls and donuts or drawing things in 3-space, but really if you want to try to formalize some of this stuff, you would actually be looking at S1 cross, the disk, if you're thinking about a torus or a filled torus. But we really think in terms of pictures and lots of that. And so sometimes it's a bit of offsetting because there's not students going into it, especially from a general topology background, don't have that same feeling of rigor. And then a couple of testimonials to this point is I was at a conference quite a while ago, and I remember talking to a descendant or someone who was very well established in the Moore style. He was a set theoretic topologist, and he tells me, wow, I took the whole semester of algebraic topology, and I could tell that the plane was different from a plane with a point missing. It has a hole in it. And it was like, he's like, what, who cares? And the other thing, this was actually another person who was potentially going to help us and be part of this class. He got a bit frustrated. Again, he's very set on having a very rigorous structure. And he felt all we were doing were just working with these examples and proving things about the examples, and he wanted more underlying structure, like a more general type of theorem proving environment. Okay. So that's a bit of the motivation, what we're looking at. So we have these two types of general topology, which is strongly associated with the Moore method, but then when you look at things like algebraic topology, it has a bit of a different flavor to it, and it hasn't been widely approached using IBL methods.
And so for this course, it was just an on-the-books course in algebraic topology that I had registered for as a first semester student. It was to be taught by Dr. Christina Cooperberg. And I was the only one registered for the course. And various other circumstances were coming up, so I got Frank and another graduate student interested, and the three of us decided to do the course together with Dr. Cooperberg. I'm in dynamics, Frank is in continuum theory, our third contributor is set theoretic topology, but none of us really had a strong background in algebraic topology. We'd all seen it a little bit here and there, and we could sort of figure out what a cycle was, and get the gist of it if we'd drawn pictures, but none of us had really had formal coursework in it. The other two students
I'd taken one semester at that point with it, but it was a lecture-based class.
Oh, okay.
Yep.
So and the two of you had some previous Moore method courses, and I hadn't. So the structure that we worked out, and Dr. Cooperberg was very flexible. She let us work out our own structure of how we wanted to do this, and so we ended up meeting 2 to 3 times per week for an entire semester. And actually about once per week into the following semester, just because we were still interested and had problems to keep working on. But we would just discuss either examples we'd come up with, examples we'd been given, and present the proofs of the theorems that we'd come up with to each other.
Okay, so
this is where the structure gets unique.
So the last one, if you notice, the subtitle was who, what, and when. So we're going to go through these basic questions that we're supposed to ask. We don't have terribly much inquiry in this, but this is one inquiry. So in doing as you can see, we have flexible structure, but okay, so where do you think this took place? Any Starbucks? It might have. Well, maybe another. Okay, Starbucks where? We're Auburn students, so probably a natural. Auburn, Alabama would be a good guess. Well, it was also taking place in Mankato, Minnesota.
I was not in Auburn for the duration of the course. I was living in Minnesota, and
it turns out that most of the semester, Christina was actually in Warsaw. She had some family things. So we were very spread out. I guess Stephen, Clonson, myself, we were the only ones. We met in a classroom, and what we basically did, we pulled up. So how did we get this done? Well, there's the email, so we'd get emailed the course notes, and of course we just get on Skype. So 2 or 3 times a week what we're doing, we're setting up our Skype cam with Jeff on the other end, pointing it out a blackboard and getting to work presenting our problems and solutions. And this is another kind of interesting aspect in this. When she did come back from Poland, well, she was still, again, sending us course topics, sending us work, and we would, send her back solutions, and she'd go over them. But every once in a while we'd get stuck, and she never really forced herself on us, but every once in a while if things got really difficult, we'd actually invite the instructor back to the class and ask her to, talk to us a little bit about this to help get us through, or maybe give us maybe a little bit more understanding, provide some examples. So the instructor in this case, so she was an esteemed and invited guest to the classroom. Okay, and so then the big question, so why did we do this?
Well, from my perspective as an introductory grad student, I was interested in applying algebraic topology to dynamical systems. And with Frank and Stephen, I think both of you had an interest specifically in persistence homology and looking at Vietoris homology, which isn't normally a component of a regular algebraic topology course. If you're going through some of the entry-level ones, it's not going to be in there.
Well, at least it's not going to be an emphasis. So again, this idea, so with Stephen and I, we'd kind of started really interested in this idea that we'd been hearing about at conferences, this persistence homology. So we wanted that. Of course, algebraic topology is popular outside of basically everyone. There's a lot of algebraic topologies applications in math. People just study it. So we just, for that reason, but also, again, we just wanted to actually understand something. So like I said, I took a 1-semester course, it was lecture-based, and really there are other reasons for this, but I really had not a very good feeling, or I was not comfortable dealing and studying homology and induced maps and things. After that course, I really struggled on a lot of things, and I just didn't feel like I had that same confidence with it. Okay, so what we're going to just kind of outline. So again, if you're looking at, and again, just a 1-semester introduction to algebraic topology, you typically start off, you study Euclidean topology, and then simplicial complexes, especially with the geometric realizations of that. And of course, you develop the idea of cycles, boundaries, and you get to the idea of homology. And then, of course, if you want to sort of understand some things about homology and use this to distinguish spaces, well, you have to, well, in this case, simplicial complexes, you have to talk about simplicial maps. You might talk about this idea of barycentric subdivision and the induced maps. And if you actually want to start applying it to sort of showing that this is a topological invariant, you have to go through quite a few steps to get to this. And usually there's this construction, either so with a check cover, but so basically taking this inverse limit, but it's very simple, but basically showing that you get a inverse limit that's homeomorphic to the underlying topological space, an inverse limit of simplicial complexes. So just from a personal experience, what was frustrating with just kind of going with this is that whenever I'm coming, again, just with a background in general topology, I wasn't used to dealing with just simplicial complexes. Jumping into this area where it's just, discrete spaces and working, or this discretization. And so I didn't feel like I could use that same intuition that I had developed coming from general topology going into this algebraic topology course. Okay, so that's my illustration of a point. Boom, boom, okay. So what I'm trying to say is that, of course, things that are very nice, easy to study, path connected. So if you take an arc, a circle, a disk, these things have very nice, obvious structure that you can relate to simplicial complexes. An annulus, two holes. But then what happens whenever you start getting to more complicated spaces, okay? And this is really my background in continuum theory and general topology. I'm used to dealing with these pathological spaces. What happens when a space its topology doesn't allow it to be path connected? So you have some examples. You have the topologist sine curve. You have the Warsaw circle or the Austin circle, depending on which side of the ocean you're on. So in some sense, and if you're familiar with shape theory, the Warsaw circle looks like it has a hole in it. It has some sort of this idea of cycle, but you wouldn't be able to find this with your standard approach from simplicial homology. And of course, you have complicated things. You have the Hawaiian earring. And then you can get even more exotic, the bucket handle, probably many. You have the Lakes of Wada. So I think probably most people here know, but it's a compact set that has two complementary bounded domains. Oh, and of course, I can't draw them, but there's also I study things called pseudo-arcs and pseudo-circles, and those are nowhere path connected. So those types of things seem almost, this idea of looking at simplicial complexes only seems like a huge restriction if you're coming from a stronger general or fundamental topology background.
But with a lot of these examples, we look at them, and actually, I just wanted to pop back. But we look at things like the Lakes of Wada, these two bounded complementary domains, and how they're, or three or four, how they're intertwined, and we start thinking of, well, here's the picture, and here's our intuition, but that's where we struggled in this course, was let's move beyond the intuition, and we know what we want the answer to be, our intuition tells us what we want it to be, but then how can we rigorously define those things, and that's what, there was actually one of the problems related to the Lakes of Wada, but with n-bounded complementary domains that we spent a good chunk of the semester on, just the three of us talking about that one problem over and over again.
Okay, so kind of just summing up what I was going over. So the appeal, so that's part of the motivation. Vietoris homology, and we'll explain a bit of how that's developed, but this can be defined and developed for any compact metric space. So you don't have this restriction right off the bat. Again, so hopefully getting a smoother transition, something you can apply to some of these pathological spaces. It's very easy to see once you get familiar with it that it's a topological invariant. It's also very similar to these ideas. Really, this idea of discretizing a general topological space or general compact metric space is also something that's closely related to this notion in applied topology, algebraic topology. Of course, the downside would be, it relies more on possibly a general topology background. We are all more advanced, so it's not entirely clear how well this would go over if you didn't have the general topology background. And it's also, again, just like, if you're familiar with things like singular homology, it's not necessarily the easiest thing to compute. So if you want to do computation, I've been told that's one of the nice things about simplicial algebraic topology. It's computation of homology works out a lot nicer on those simplicial complexes.
So in the Vietoris, we wanted to just give you a few slides to kind of show you how the theory was put together. We start with this notion of an abstract simplicial complex. So instead of the usual geometric simplicial complex that a lot of students see in their examples, where here's vertices and here's edges and here's faces and I can draw all of it, we go into an abstract simplicial complex, just a collection of finite non-empty sets where all the one-element subsets are in there, and if you've got something in the complex and it's got a non-empty subset, then the subset's in the complex, and we build this abstract simplicial complex from there. Take finitely many sums, and we may or may not introduce, we would induce orientation. But we started with really simple examples, right? The same kind of examples you would see in a very picture-based algebraic topology course, and given problems like the one we've got up here, trying to figure out what are cycles and what are boundaries of straightforward complexes. But then we move it on in general. Oh, sorry.
So it really does. I mean, you start off on those same basic things. This finite, discrete type of object that you apply or that you associate with a space. But then the very next thing. So when you get to the Vietors complex, and so right here is where you break, and you essentially get a lot of your generalization with doing this. So we define for all those ideas in the abstract case. Chains, cycles, boundaries. So we define this, but we do it with respect to the metric. And so for epsilon greater than 0, we denote this Sx of epsilon as the abstract simplicial complex consisting of all finite subsets of diameter less than epsilon. And again, so right away, this is going to be a huge space. It's kind of overwhelming, but it turns out that after playing around and getting some familiarity with this, you realize a very quick connection with what you're doing in the abstract case or the simplicial case. So just an example. I'm not sure. I guess we won't go over too much of this, but one thing that you can do just to play around with these things. So and this is pretty accessible. So just to get familiar with the definition. So what is if you have an annulus like this, so it's a unit square with again a chunk that's 1/3 by 1/3 taken out. Okay, can you find the greatest positive number, so that there's a D cycle that is not a D boundary?
So a covering of this thing with these sets of diameter D that actually forms a cycle. So you start with one and chain along to get back to the other, but then it's not going to be just a boundary.
So it's just, right. It's interesting, but what it starts getting at. So you play around with this notion, the definitions. You play around with this, but then you start realizing, okay, it really does matter on this metric. If you take the slightly smaller hole, you realize there are these cycles. You can kind of recognize these cycles that aren't boundaries. However, if your mesh isn't small enough, you may not pick up everything that you would recognize as being a hole or being a cycle.
And as we continue to introduce more holes just of the same size, or continuing on for forever and ever until we get this lovely carpet, trying to figure out what's going to happen. And we started with just one hole, 5, okay. Started with just one, moved to many, and we start building this sequence of these diameters we ended up having to look at. And the notion that came along with this, we started looking at homologous cycles. And this was another place for anyone who's interested in using this approach where we got stuck for a long time. The notion of if you take two of these cycles and look at their difference, and is that difference a boundary? It's another one that comes very quickly if you're looking at just the pictures. But when we started trying to discretize, I think that was the word you were using, to discretize this. And
formally prove these.
And formally prove these things, we got stuck. And these things took us a really long time to get our notation put together in such a way that we felt this was rigorous and complete. And so here's an example problem that we used to motivate, or that this problem was given to us to motivate the notion of homologous cycles. And we could start with, what I've got outlined in red. If I don't have the arrows on here, but if I had an orientation, this could be a cycle. And the intuition we worked with was the notion that I could sort of, by pushing this thing out towards the outside edge, tack more and more stuff on, right? So I want to tack on that edge, so I fill it in, and it removes what I've got left in the center. And I just continue that process all the way around. And I can see that, I can see the picture, I understand what's going on, but getting nice, formal, crisp notation that's going to be true, not just for this particular example and for that one particular cycle, but for an arbitrary cycle was the sort of problem that we really struggled with, and it took us a long time to get those things put together.
And there's also, so it's basically used the same type of pushing method, even in this general case, in this Vietoris case, and it actually turns out once you again get that intuition, it actually gives you a bit of flexibility, because you can create these these simplices from just arbitrary set of points in the space, and so it actually gives you, whenever you're doing the arithmetic, it actually gives you a little bit of flexibility when you're trying to prove these things. So that was actually kind of a nice surprise. I think since we are short on time, so we want to get through, I'll put everything on here, but the whole idea, so all this comes into play. So we talked about an epsilon simplex, or epsilon cycles and epsilon boundaries. Well, really the key of this, where you get this nice thing of picking up the shape of just these arbitrary spaces, comes with whenever you define the Vietoris homology, you actually do it with infinite chains and cycles. And so what you can think of these things as being as a sequence of chains of cycles, so that they decrease the mesh of those simplices, or the diameter of the simplices decreases, however they're all homologous to each other in this sequence. And it's that aspect that you're shrinking that mesh size, so it's automatically picking up a higher, how would you say, basically a greater resolution, you can think, and picking up these tiny holes in here, the smaller holes in these compact spaces. And everything goes, it's really the same, everything's defined the exact same way as a simplicial approach. But again, you're seeing, after playing around with this, when you're dealing with things like the Sierpinski carpet, so when you're dealing with these things, you realize it's that the fact that you're defining it with this long sequence, you're able to pick up these smaller holes in here and actually get something that you can define and work with. Well, I guess we'll open it up to questions, but basically this was what we covered. Remember, this was only a one semester course, so the whole intention, so there's lots of things that you would probably think from a standard introduction to topology, exact sequences, some cohomology, that relative homology, that wasn't covered, but the whole idea was really just to give a rigorous introduction, or a solid foundation in a one semester IBL course.
And I guess my takeaway from this as a student who'd never had an IBL course before was that IBL makes you stronger.
So anyway, so that's, yeah, and helps you grow hair, right?
And helps you grow hair, yeah.
Anyway, so thank you, and we'd like to thank, again, the generous support from the EAF. They did help Christina Cooperberg in funding this project. They've also supported our travel here, so we're greatly appreciative of their work and everything that they've done for inquiry-based learning. Thank you.
Hussein Al-Turki, University of Oklahoma. What are the differences between this class and any other reading course?
So, well, reading course in the sense of typically, well, we didn't have any proofs. We weren't looking at a written proof or idea. So we were just basically just given examples and theorems. So it's closer to that that more method where you aren't exactly trying to read and understand a proof that you might see in a text or paper or something like that, but just coming up with it on
the pages that we were given, and for each of these 8 chapters and the 5 appendices, it was maybe 2 pages, front and back, just very terse definitions and then problems to work out from scratch. So there wasn't a lot of reading to be done. And as someone who never had an IBL course, my first instinct was, well, maybe I can find another book that'll help me explain these sorts of things, and I couldn't find anything.
We tried to be pretty good. I guess especially with Stephen and we kind of would wag our finger at him whenever we heard him talking about, well, I think this is similar to such and such in this text, and we're like, no, we can get this, we can get this, we can get this. So a lot of that, there was probably more time spent struggling with some of the definitions and everything, just making sure that we had the correct idea. So coming up with our own examples and trying to determine that we're working through this correctly. Those are the times when, of course, when we were really struggling, we would ask, Christina for some feedback and input. And so, but again, when she's in Poland, we get, 2 or 3 sentences. Why don't you maybe take a look at this example, or have you considered this? And that was it. So it was really, not too much to sink your teeth into from the professor.
Hi, Nag from Black Hill State. It's the way you introduced that you went from general topology to algebraic topology. What was the motivation to go to Vietoris homology, not like check structure? That would be like from general topology.
That's right.
It would be more natural.
Well, it really is, and if you're familiar with check homology, you really see this kind of intermediate. So you can kind of have simplicial, usually use some sort of like check complex to do this approximation when you're trying to show like topological invariance, and you get that. In this case, it's kind of on the other extreme. You don't have this. You basically, whenever you pick up these fundamental cycles, it's kind of doing everything at once whenever you're looking at these. So there are 2. Aside from just being able to apply these to general spaces, there's the other aspect. One thing that Christina and some of her colleagues have picked up on, there's been a lot of talk with all these new trends in topology. I mean, this was stuff that was actually done in the 1920s. Yeah. So this was done, also gets back last year. I didn't hear too many talks about it this year, but last year, a lot of talks about learning from history. Okay, this is a very strong, and it's a very natural, a lot of times you find these historical methods, they're more natural coming into it than after years of formalization and refinement. So that was kind of the idea. Let's look at a more historical approach and try to see how that develops, if we can get a more natural understanding of it. So that would be another.
The second question was that, so are you guys using this for in computing persistent homology and stuff like that? Is that the motivation?
This is, I guess, so not currently. So I think, especially Steve and I, we have interest in that area. We wanted to learn more about it, but of course we needed some sort of understanding of algebraic topology. So we did not go to that extent yet. In one of the appendices, there's just a very brief introduction. It's actually, while we're here, any feedback on if we were to continue, or if Christina was going to continue trying to develop these course notes, what might be really great to develop in a 2nd or 3rd semester type course, so a follow-up. And that might be one of the things, looking at developing that idea towards the applications a bit more. But no, we are not currently, applying.
And last question, where can you get these notes?
So email us. Let's see.
I think
there you go.
I'm in his email group, I think.
Yeah, so you got an email from me yesterday after the roundtable.
Yeah, right, yeah.
So
maybe I'll email you.
Shoot me one, and then I think that was from a different school address that's different from that one. But either one will work, and then I can get you the notes.
So we do have a PDF, and we should, Christina usually points this out when she speaks about it, but this was just for the picture. There's actually not a physical copy like this. It was just a nice, I think she took a photo at Office Depot or something, and then copied it on. But anyway, but this is what our end goal. We're working to develop some course notes like this, but we do have PDF drafts.
Okay. So I'll send you an email.
Hi, Tom Hall, Western New England University. I think that kind of asks my question now, which was, did Christina develop these notes beforehand or as this was going on?
This was an ongoing process. And so, again, it was back and forth with the feedback. She would, and this was really the part where we would just get these statements or theorems or examples, and sometimes you're like, well, this example isn't really clear. Sometimes we'd come out with our own examples, and we'd have to ask her, and she was like, oh yeah, that would be really good to have maybe put as a side note or something that maybe if, try this and this and this. And so that was this was a whole work in progress.
And as we went through it, Frank and Stephen were there just for their own edification. I was actually an enrolled student in the class taking it for credit. So once we felt like we had a solution, it was my job to type it all up and send it to Dr. Cooperberg so that she could review our proofs and look for where we may have needed a better hint and that sort of thing. And actually, at the end of the semester, we all did just over email a debrief of what did and what didn't work and where we struggled the most, and passed that information on.
And I think that's still kind of getting in the process of getting incorporated into the notes. Anyway.
Well, thank our speakers.
Thank you. Thank you for coming.